Hello, assalamu alaikum. How are you today, guys? Well, today we are going to talk about a new concept. It's called isomorphisms. Well, we talked about linear transformations. So here, let us recall a few things. When you have a vector space U, and here you have a vector space V, we defined linear transformations between vector spaces. So let's say here T is a linear transformation. Okay, so number one here, T is a linear transformation. T from U to V is a linear transformation. We talked about this linear transformation is one-to-one if and only if the kernel. So here is the kernel. What do we mean by the kernel? We mean by the kernel all vectors in the domain that are mapped to the zero vector in the range. So here we see which vectors here are mapped to the zero vector here. So here is the kernel. This is the kernel of T. So T is one-to-one, is one-to-one, if and only if kernel T has only the zero vector. The kernel is a subspace, so here it is the trivial subspace 0. 3. We talked about the range here. And we said here the range of T is related to whether T is onto or not. So here T is onto if and only if range T range T equals V. So if the range of T covers all of V, in that case, T is onto. Also, since we are doing our job in finite vector spaces, we said nullity of T, which is dimension of kernel T, plus rank of T, which is dimension of range T. That is the dimension of domain T. Dimension, domain T. So this is a very important theorem here. It says, in other words, nullity of T plus rank of T equals the dimension of the domain, which is U. Okay, so we discussed all of this. We gave examples about all of this. Now, if we have a linear transformation that is one-to-one and onto, we call that linear transformation an isomorphism. So here, if T from U to V is linear, 1, linear, 2, linear transformation, 2, one-to-one, 3, onto, then T is called an isomorphism. It's called an isomorphism. And U and V are called isomorphic vector spaces. What is interesting about two isomorphic vector spaces here, Basically, they are like photocopy of each other. They are comparable. From algebraic point of view, they are comparable. What you do here is comparable to what you do here. So in reality, you can think about this when we give you an exam and we give you different versions of the exam. So here, when we give different versions of the exam, we try to make it comparable in terms of fairness, difficulty, number of points, the needed time. So we do our best to make it comparable. So that is like isomorphic here in vector spaces. Okay? Or if you think about those who are interested in astronomy here, when you talk about planet Earth, and if you think about there is another planet that has similar conditions like Earth, in that case, we can say we are looking for an isomorphic planet. It is a planet similar to our planet. In vector spaces here, that is very interesting because what you do in this vector space is comparable in some sense to what you do in the other vector space. Okay? So basically here when we say a linear transformation is an isomorphism, it means you have to show the kernel is the trivial subspace 0, and you have to show the range is the same as the codomain. So here V is the codomain. Now, this one you can do it from the kernel, and this one you can benefit from this theorem, because if you know here the nullity or the dimension of the kernel, and of course you know the dimension of the domain, so in that case you can find the rank, and if the rank is the same as the dimension of the codomain, then in this case it is easy to prove that it is onto. All right, so after clarifying the concept, the definition, and a motivation for that, let's take some examples. And as usual, I start by an easy example here. All right, so here is example number 1. Define T from P2 to R3 as you take a polynomial here, ax squared plus bx plus c, and you send that into a, b, c. I'll leave it for you as an exercise. You already know that, but you can double check again. This is linear. T is linear. Okay? Now, let's see, is this 1-to-1 and onto? Well, what is the kernel here? The kernel T is all polynomials in the domain that are mapped to the 0 vector in the range. Now, what is that? T of B is 0, 0, 0. It means A is 0, B is 0, C is 0. So what do you have here? So that means it is the 0 polynomial. So yes, T is 1-to-1. So T is 1-to-1. 3. All right. We want to show that T is onto. How do you show that? Well, you can use here your pre-calculus ideas. You can take here arbitrary vector in the codomain here, and you can see that ax squared plus bx plus c in the domain is mapped to this. Okay, so that is the pre-calculus way of doing it. Or you can use the linear algebra way to do it, which is use nullity and rank here. Well, the nullity here is 0. So here nullity is 0. What is the rank? The rank is going to be nullity plus rank is the dimension of the domain. So rank of T is going to be what? It is going to be, what's the dimension of P2? It is a 3. 3 minus 0, and that is 3. Now, what is the dimension of the codomain? It is a 3. So from here you can see 3, dimension of R3 is a 3. So the range is going to cover the whole codomain. So there is nothing left outside here. Okay? Hence, that is dimension of R3. And this means, hence, T is onto. Now, it is one-to-one, it is onto, it is linear. So this linear transformation is an isomorphism between those two vector spaces. And those two vector spaces, they are isomorphic. Hence, T is onto. So T is an isomorphism. Let me tell you something here. I've seen some students, when we ask them to check whether certain polynomials are linearly independent or not. For example, is B equals, let's say, x squared plus x plus 1. Here x squared minus 1. And here 2x minus 3 is linearly independent. Is a linearly independent set. Is B a linearly independent set? I've seen some students, they take the determinant of this matrix 1, 1, 1, 1, 0, negative 1, 0, 2, negative 3, and they see whether this determinant is 0 or not. And if the determinant is not 0, they say those three polynomials are linearly independent. And I used to ask them, why is that? Well, think about it. When you talk about those polynomials, you talk about them in P2. When you talk about those columns and you take this matrix, you are talking about vectors in R3. So why? Why is this going to tell us whether those are linearly independent or not? Those are vectors in R3. Those are vectors in P2. The reason you can do that, because this and this, they are isomorphic. Isomorphic, and here is the isomorphism. So the right way to do it here, if you want to use this to check whether they are linearly independent or not, before that, you should say, because this and this are isomorphic, and this is the isomorphism, then instead of those, we can take those vectors and check whether they are linearly independent or not. Okay, so that is the right way to give a complete justification for what you are doing. Okay? All right. Now, from here, actually, you can generalize this and take it not only from P2 to R3, you can take it from Pn to Rn plus 1. And in the same way, I'll leave it for you as an exercise. You can take an xn plus an minus 1 xn minus 1 plus a1x plus a0 is mapped to an minus 1 a0. This and this, they are isomorphic, and here is this is an isomorphism. All right, so far we are talking about kind of easy examples. Let's take something that is more interesting. Example 2. I'm going to define T from P3 to R4 to P4. As T of Px equals x Px. We already discussed this example before, and we checked this as a linear transformation. If you forgot that, you can go and double check again. This is a linear transformation. Now, is T 1 to 1? 1. Is T 1 to 1. 2 is T onto 3. Is T an isomorphism? All right, so let's address those questions here. As you know, to check whether it is 1 to 1 or not, the easy way to do it is just look at the kernel. Of course, you can again use here the precalculus way of doing that, but we're not interested in checking it in that way. Let's here think about the kernel. What is the kernel of T? 1, kernel of T is all polynomials in P3 such that x px is the zero polynomial. Now, you want x px to be 0. Now, we want this to be true for all values of x. Don't tell me here you want to take x equals 0 and that's it. No, here, we're talking about for all values of x, all real numbers. So in that case, the only option is to have px equals 0. And in that case, you are going to get only the zero polynomial. So from here, you can see 1 to 1, yes. And here is the justification. Okay, what about 2? 2. How do we check? Is T on 2? We have to see the range. Is the range going to be all of P4? So how do you do that? You see the rank. What is the rank of T? Well, rank of T is dimension of the domain, which is 4, minus the nullity. What is the nullity? It is 0. Now, this is different from dimension of P4. What is dimension P4? Dimension of P4 is 5, because this is 5, this is 4, so they are different. So basically what happens here, you are not covering all the codomain. So here, when you go back to this and you think about this as P3 here and this as P4 here, so what you are covering here when you take xpx is part of P4, not all of P4. So let me ask you here, what is missing outside? So what is left outside here? xpx. You are missing the constant polynomials here, correct? So the constant polynomials, so this is x here. It goes to x, this is px. It goes to xpx. So here, constant polynomials are missing. Constant polynomials. Constant polynomials, they are out of the range here. So the answer here is no. And in this case, is this an isomorphism? No, it is not an isomorphism. This is not an isomorphism. Okay, let's make it here more interesting. So here, question number 4, find a basis for range of T. Remember, range of T is a subspace of the codomain, correct? So the kernel is a subspace of the domain. Let me stress that here. The kernel is a subspace of the domain. And here, the range is a subspace of the codomain. Always keep that in your mind. So when we talk about the kernel and the range, they are subspaces. Okay? The kernel is a subspace of the domain, the range is a subspace of the codomain, and at any point we can ask you find a basis for either one of them or for both of them. So here, find a basis for the range of T. Well, you need to understand the range here. We already said here, you cover all polynomials that are non-constants. So from here, you can see range of T is going to be ax multiplied by ax squared plus bx plus c, such that a, b, c are real numbers here. That is the form of the general form of the vectors in the range. And from here, you can see that this is a span of x cubed, x squared, x. And x squared, x cubed, they are linearly independent. So basically here, b equals x cubed, x squared, x is a basis for the range. It's a basis for the range of T. Oops, no, I'm sorry, I'm doing a mistake here. I'm talking about vectors in P3, so that should be here x cubed, this is x squared, this is x plus d here. And here there is also d. So this has to be here x exponent 4, x cubed, x squared, and here is x. And now here I have to put also x exponent 4. X exponent 4, x exponent 3, x squared, x is a basis for the range of T. As you can see here, we have 4 vectors in the range. And that is consistent with what we said here about the rank. Okay? All right. So now I am going to make my example interesting in the following sense. I am going to remove this, and I'm going to put here the span of those. So here, from P3 to span of x, x squared, x cubed, x exponent 4. In other words, I removed this part here, and my range is becoming this, let's say here, V. This is my range. Is T 1 to 1? Is T onto? The same questions here. Is T an isomorphism? Well, 1 to 1, obviously, it is the same thing here. It's 1 to 1. Is it onto? Well, we removed the problematic part here, correct? It is like in pre-calculus when you take, for example, sine x, or when you take fx equals x squared, and you take this from R to R. This is not onto. But when you restrict here the codomain and you make it 0 to infinity, then it becomes onto, correct? All right. So here it is the same thing. We removed the problematic part here, and now our range is the same as the codomain. So in this case, it is onto, correct? So now, this, from this vector space to this vector space, a subspace is a vector space by itself. So this and this, they are isomorphic. And here is the isomorphism between them. Okay? So this is yes, and this is yes. So here, when your range, when your linear transformation is not onto, but it is 1 to 1, you can remove something from the codomain to make it same as the range, and in that case, you can make it onto, and in that case, you get an isomorphism. So here, if the range is a proper subset of the codomain, then there is a subspace in the codomain, which is the range, in which you have an isomorphism. Okay? All right. Let's take one more example. Or let's make here a conclusion. Then we can take more examples. Theorem: if U and V are vector spaces of finite dimension, then they are isomorphic. Then U and V are isomorphic. If U and V are vector spaces of finite and equal, finite dimension, such that and equal dimension, then U and V are isomorphic. Why is that? Well, they are of finite dimension. So here is a vector space U, here is a vector space V. Now, here you have a basis. Let's say our basis here is U1, U2, UN. Here we have a basis. Let's say here V1. It's of equal dimension. So V1, V2, up to Vn also. Now, any vector here can be written as a linear combination of those, correct? So if you have here X, then X can be written as C1, U1 plus C2, U2 plus Cn, Un. And if you relate now those vectors here with those vectors here, U1 goes to V1, U2 goes to V2, and Un goes to Vn. It means when you take here T of X, that is going to be T of this. And in this case, you can make this as C1 TU1 plus C2 TU2 plus Cn TUn. And in this case, TU1 is V1. So in this case, we make a linear transformation that is one-to-one and onto. And I'll leave it for you to convince yourself or double check that. So you can see here the kernel, the zero vector goes to the zero vector. You can see it is onto, and in that case, this is indeed an isomorphism. And from now on, whenever you have two vector spaces of finite and equal dimension, you can say they are isomorphic, and it is very easy to construct an isomorphism between them. Okay, use this idea, you get an isomorphism. All right, so let's see here. M2 by 2 is isomorphic to P3. Why is that? This has dimension 4, this has dimension 4. Now, can we construct an isomorphism between them? Yes. Take T of T from M2 by 2 to P3 as T of A, B, C, D equals AX cubed plus BX squared plus CX plus D. We are using this idea. If you think about what you have here, we are using this idea. We are relating this 1, 0, 0, 0 with T of this is this. Correct? T of 0, 1, 0, 0 is x squared, and so on and so forth. So this is linear. It is one-to-one. It is onto. So this is an isomorphism between those two vector spaces. Can you think about other isomorphic vector spaces? You can realize this. So if you take n by n here, you can make this what? N squared minus 1. Correct? N by n, here you need n squared minus 1. What if I take this m by n? This should be mn minus 1. Okay? And we know this is also isomorphic to R4. So this, you can make it now isomorphic to R4. So here when we say there is an isomorphism, it doesn't mean it is only one isomorphism. Each student or each one can construct his own isomorphism. Okay? As long as it is linear, it is one-to-one, it is onto. Because it's one-to-one and onto, and you can even reverse the process. So instead of taking this from M2 by 2 to P3, we can take from P3 to M2 by 2. We can reverse the process. It is an isomorphism. So let me write this as a remark. F, and that's obvious remark, F T from U to V is an isomorphism. Then T inverse from V to U is also an isomorphism. Okay? All right. Let me take one more example and I'll stop. Let me take this one. I'm going to define T from P2 to P2. T from P2 to P2 as define T from P2 to P2 as T Px equals P2x P2x plus P1. Is this one-to-one? Is this onto? Is this isomorphism? Look here, don't rush to look at this and see here P2, P2, so it is going to be an isomorphism. No. Yes, P2 and P2, we know they are isomorphic, but it doesn't mean that this one is the right isomorphism. Okay? So here, you need to check, is it one-to-one? Is it onto? So let's do that. Number one, kernel of T, or before that, do you understand what's going on here? So here when you take T, ax squared plus bx plus c, polynomials in P2, the image of that is going to be what? That is going to be P of 2. So that is 4a plus 2b plus c into x plus P of 1. That is a plus b plus c. So here, if you want the kernel of T, that is going to be all polynomials a x squared plus bx plus c, such that this is 0, which means 4a plus 2b plus c is 0, and A plus B plus C equals 0. So here, you need to think about all polynomials in which the coefficients satisfy those two equations, correct? Well, here you have three coefficients, three constants, but here you have two equations, so you need to solve this homogeneous system here, correct? So when you solve this, you can solve it in any way you want. Quickly, we can say here C equals negative B minus A. And from the first equation, you get 4A plus 2B minus B minus A equals 0. So from here, you get B equals negative 3A. Am I correct? B, and here 3B, move to the other side, negative 3B. So B is negative 3A, and C is negative 4, negative positive, so that is 2A. Let's double check here. Negative 3A, negative, okay. Yeah, that seems to be right. So here the kernel is going to be ax squared minus 3ax, and here plus 2a, such that a is in R. And what is this? This is going to be span of 2 minus 3x plus x squared. So the span of this vector is going to be mapped to the 0 vector in the range. So here the kernel is not the trivial subspace. What is the dimension of the kernel? The dimension of the kernel is 1. So the nullity here is 1. So it's obvious that this linear transformation is not onto. Hence, T is not 1-to-1, is not 1-to-1. Also, it's obvious it is not onto, because we are talking about P2 here, and here you will not get quadratic polynomials. So it's obvious that it is not onto, and also you can conclude it is not onto from the rank and the nullity here. All right, so this is not an isomorphism. All right, so let me ask you a question here. Question? Consider T from R4 to R4, or R3 to R3, R3 to R3, defined as T x1, x2, x3, 3, x1 plus x2, negative 2, x1 minus 4, x2 plus 3, x3, 5, x1 plus 4, x2 minus 2, x3. So this is from R3 to R3. Is this an isomorphism? Is T an isomorphism? Well, I'll leave it for you to do it, but let me give you here a hint. If you think about this, what is this here? This is 3, 1, 0, x1, x2, x3, negative 2, negative 4, 3, 5, 4, negative 2. So this here transformation is actually a matrix transformation. So here when I talk about this, well, you can take this matrix A and just think about the matrix A. Look at it. It's just a matrix transformation. Remember, we said every matrix is a linear transformation. So here, this is A from R3 to R3. A takes x1, x2, x3, and it gives you that vector 3, x1 plus x2, blah, blah, blah. So basically here, we are talking about a matrix transformation. Now, this matrix transformation is one-to-one add onto if and only if this matrix is invertible. So here when we ask you, is this an isomorphism? All you need here is, ask yourself, is A invertible? In other words, what is determinant of A not 0? That will tell you whether it is one-to-one and onto. So a question like this should not take from you more than 1 minute to address. Okay? You don't need to spend too much time trying to do all the technical details. Right away, you can jump to the determinant and see is the determinant 0 or not 0. If it is not 0, then it is invertible. Then it is one-to-one and onto. Then it is an isomorphism. Okay? All right, so I'll stop here and please do the exercises about this. And if you have questions, please feel free to contact me and we can discuss them in our live session. All right, have a good day, guys. Bye-bye.